Hello everyone, welcome to the mathematical lecture series on foundations of algebraic structures and number theory. In today's discussion we are going to talk about Euler's theorem. So as a continuation of various theorems connected with congruence, so in this discussion we will be talking about Euler's theorem. So if there is any integer a and it is a finite term, we can say that we can write a power phi of n is congruent to 1 mod n, where this phi of n is the Euler's phi function. So Euler's theorem generalizes Fermat's little theorem to any integer n, just not primes. So apart from prime, for non-prime members also we can use Euler's theorem. So it acts as an important concept in congruence concepts in prime number and congruence ideas. So suppose if you say a equal to 2 and n equal to 9, okay, n equal to 9, then phi of then you can write as a congruence relation, that is 26 congruent 1 mod 9. So phi of 9 equal to 6. So what I'm trying to say is, if you are going to work with Euler's theorem, you should know the clear idea about Euler's phi function. Euler's phi function works on that integer and tries to understand the number of positive divisors of that particular number. For example, if you take an integer 12, then the number of elements, that is number of divisors for the 12, can be counted. So all those terms, for example, if you take 12, you have what are the terms you get at divisors for the 12. So you can take that numbers and you can try to understand the GCD between the divisors and this number, so which are all relatively prime, you can understand, and those terms can be used as a outlet, as an outcome of that Euler's phi function. And this concept, to the next level, it is connected with Euler's theorem. So that is how we work on Euler's idea. So if you are very clear in this concept of theoretical manner, you can go for solving problems. So you can compute values, of some numbers with which is suppose it may be a prime number, may not be a prime number. To that number you can find the number of positive divisors, and you can understand the modular exponentiation concepts involved in that, and you can see the connection between Fermat's little theorem and also this Euler's theorem. So there is a connection between, always there is a connection, because all these theorems are working in congruence area. So since they are working in prime numbers and congruence areas, so Fermat's little theorem plays a very important role. So Wilson's theorem, Fermat's little theorem, to the next level Euler's theorem plays a very important role. And also in specific, Euler's theorem can be used upon prime number, also non-prime numbers. So that Euler phi function plays a very important role in Euler's theorem. For instance, suppose if you say n is prime, then phi of n is n minus 1. It is n minus 1. For a composite number, phi of n is calculated by using its prime factorization. So for example, if you are going to work for phi of 9 or phi of 10, when you solve those concepts, you will clearly understand what I try to mean here, and you can connect this Euler's phi function with the Euler's theorem. What it is really trying to connect with. So in this congruence idea, this is very important to connect with. So Thank you for listening. So Euler's theorem plays a very important role in cryptography. So for more knowledge, more ideas, you can still browse more into this. Thank you.